Okay, so now this is an interesting question, conceptual problem also. A body of a constant heat capacity Cp and at a temperature Ti is put in contact with the reservoir at a higher temperature Tf. The pressure remains constant while the body comes to equilibrium with the reservoir. Show that the entropy change of the universe is equal to this one. Now, you see we are talking about entropy change of the universe. So, entropy change of the universe is equal to entropy change of the system plus entropy change of the surrounding, and we have to calculate both of them. So, here the heat capacity is Cp and temperature is Ti, in contact with a high temperature Tf. So, what is the change in the heat that we see, reversible heat? How does that? So, it is a constant pressure process, right. So, how does the heat change in a constant pressure process? So, we know that dq reversible is TdS, right. We start from there. dq reversible is Cp dt for a constant pressure process is ds. So, therefore, S is Cp ln T, but we are doing an integration, right. We are doing an integration from Ti to Tf. So, S will be the or change in S will be, because we are talking about change from initial to final. So, delta S, that is why I have given it is Cp dt going from Ti to Tf. So, it is Cp ln Tf by Ti. Okay. So, this part is okay. So, this is the part of the system's entropy change. How did I do that? We calculated the dq reversible and we know that dq reversible is Tds, dq reversible we know Cp dt. So, Cp dt and then put the T down and it is Cp ln Tf by Ti. This is the formula for constant pressure process when to calculate the entropy of the system. Now, what will be the entropy of the surrounding? So, surrounding however, gives away the heat dq, right, and its temperature does not change. The surrounding is the reservoir, reservoir's temperature does not change. So, q that is gone out of the reservoir is minus Cp Tf by Ti. Is it okay? What do you think? What is the dq? dq is Cp dt, right. How much heat is going out? Heat is going out according to heat capacity and temperature difference. How much heat was going into the system? System was Cp delta T. Now, what is the entropy that the system is the surrounding is going to lose? Cp Tf minus Ti by Tf, because Tf is the temperature of the reservoir. What is the formula for entropy? dq by T, right. What is dq? Cp dt. So, we did Cp dt and we did by Tf. So, this is the, so now what is the total change? The total change in entropy will be Cp ln Tf by Ti minus Cp Tf minus Ti by Tf. Now, what is x given here? X is minus Tf minus Ti by Ti. So, it is this particular quantity minus this is this particular quantity. So, we can write it is Cp ln Tf by Ti plus minus Tf minus so plus Cp into x. Now, let us simplify this one a little bit more, 1 plus x. So, I add 1 on both sides. So, this is Tf, sorry, 1 plus x if I add, then it will be 1 plus 1 minus Tf minus Ti, this one, which will give us Tf minus Ti plus Ti. So, Ti by Tf. Now, ln of 1 by x, ln of 1 plus x will be ln of Ti by Tf. Okay. Now, for ln you know that if I take negative sign, it will be just the opposite. So, minus ln of 1 by x 1 plus x sorry is ln of Tf by Ti, which is here. So, this is minus Cp ln 1 plus x plus Cp x. Now, Cp is common, x minus ln of 1 plus x, and that is what is told us to prove. Is it clear? Correct. So, why in this case we did not integrate, and we have done that, right. So, surrounding temperature was always Tf, surrounding is losing some amount of heat Q. So, we are only calculating how much surrounding is losing the heat. So, system is receiving the heat in a slow manner and its temperature is also changing, that is why the integration is required on the left hand side. The integration, you see the T is under the integration sign dt by T, because at every instant the temperature of the system is changing from Ti to Tf, slow manner, but the temperature of the surrounding is always kept at Tf, it is just giving away some heat. How much heat is giving away, that is what we are calculating here. Once we calculate the heat, we are dividing by the temperature, and for the surroundings, since it is so big, we do not really care. Remember, the entropy of the surrounding is just Q by T, nothing else. It is just calculate the Q, divide by T will be the entropy change of the surrounding. So, we are calculating how much heat is lost, which is Cp delta T divided by T. There is no change in the temperature for the surrounding. However, there is a change in the temperature for the system. System is gaining the temperature slowly from Ti to Tf, and that is why we have to do the integration from Ti to Tf, which is not required for the right hand side. Good that you asked. Now, is this clear? That is the big difference between system and surrounding. I have a system which is at kept Ti and this is Tf, and heat is coming in, dq heat is coming in, system temperature slowly changes, increases to Tf. Surrounding temperature does not change, surrounding is losing some amount of heat. So, that is why it is just heat by T, and the left hand side we have to do an integration, because it is a process in which the temperature increases. Okay. So, calculate the entropy change for phase change, which is very simple. So, we are the question is that calculate entropy when 1 gram liquid water is changed from 1 gram of changed to 1 gram of vapor at constant temperature of 373. So, at 373 you know the liquid and vapor will coexist. So, all that we need. So, what is the dq? dq reversible or dq is nothing but delta the heat of the enthalpy for transition. So, enthalpy for transition is typically, we know that in thermochemistry we have talked about it, 40.66 kilojoule per mole, that is the heat of transition, right. So, what will be the change in entropy? It will be nothing but this by temperature. Now, we have to calculate the transition enthalpy for 1 gram. We know that 1 mole contains 18 gram. So, it is 40.66 by 18 kilojoule, and then you have to multiply by 373, then you will get kilojoule per Kelvin. This value will come out to be approximately 6 kilojoule per Kelvin if you do the calculation. Okay. So, here it is very simple, because we know that these transitions enthalpies are calculated at constant pressure, right. So, and we know that heat at constant pressure is nothing but enthalpy. All that we are doing is that we are calculating the total change in heat, we are assuming that it is going very slowly. So, and the temperature is not changing. So, it is just an isothermal process, temperature is not changing. So, no integration, nothing is required. So, whenever we heating the system, we do Cp ln T F by Ti, but if there is no heating, no change in temperature takes place, all that we need is the heat change divided by the temperature will give you the change in the entropy. Now, let us say you have to take the system from 15 degrees centigrade, water at 25 degrees centigrade. Let us say we want to calculate the entropy for the system when it is water at 110 degrees centigrade. So, we have to calculate the entropy change from water going from 25 degree centigrade to 100 degree centigrade in a slow manner by using CPLNT formula. At 100 degree centigrade, we will have to now add the transition enthalpy, that is the vaporization, the latent heat of vaporization or transition enthalpy, and then again there will be a CPdT. We need the specific heat of the vapor, and that will take us from 100 degree centigrade to 110 degree centigrade. So, by 3 steps we can calculate the overall entropy change going from 25 degree centigrade water to 110 degree centigrade water vapor. Okay. Is it okay, this part? Okay. So, now let us calculate the entropy of mixing. So, let us say initially some A molecules are confined to a volume Va at some temperature T and pressure P, n a number of molecules are there, and on the other side or in a different box also you can say N B molecules are there, and suddenly they are mixed, or at some point they are mixed, and then the total volume becomes V A plus V B, total pressure becomes P, and temperature remains the same. So, it is an isothermal mixing. So, what is the change in entropy for both the systems? So, we can say we can calculate that by changing the change in entropy of system A. So, system A, if you see, if you just do not look at the part V, we do not look at this part, then it is going from V A to V A plus V B, right. So, what is the formula for that expansion is minus it is minus, it is plus N A R ln V A plus V B by V A. Change in entropy for B is N B R ln V A plus V B by V B. We can call that overall volume as V also, but so now total change in entropy will be delta S A plus delta S B, giving us N A R ln V A plus V B by V A N B R ln V A plus V B by V B. Now, we can simplify this further by using, since it is an ideal gas mixture or perfect gas mixture, we can simplify it further by knowing that if I use the relation that P is the pressure, V A, P V equal to N R T. So, N A R equal to T, right, equal to temperature, which is same for the other system also, P V B N B R. So, equal to P V A plus V B by N A plus N B R. Now, if I use this relation, then we can get P P cancels of course, and then we get V A plus V B by V A equal to N A plus N B by N A. So, we can write as N A R ln N A plus N B by N A plus N B R ln N A plus N B by N B. Now, just take the, since it is a logarithm, we can take the minus sign. So, minus N A R ln N A by N A plus N B, which is nothing but mole fractions of this thing, let us call it X A, plus again take minus N B R ln X B, same manner. Let us remove this part and write it here, that delta S then. Now, let us take R common, minus R common, and also take N common. We will get N A by N, which is of course mole fraction ln X A plus N B by N ln X B. Now, N A by N is also X A, right. So, minus N R, I am just simplifying it, X A ln X A plus X B ln X B. So, that is the entropy of mixing formula. Now, this we can generalize to multiple mixtures as well. So, let us say there are multiple gas molecules are mixing, then overall we can write as N R sum over I X I ln X I minus N R. Okay. So, we can see that if X I's are half, then we will get a famous formula, half ln half will give our N R ln 2. So, that is a mixing of entropy when like volume goes just the double of that. No, so that is a good question. So, minus N R X I ln X I, but X I is a fraction quantity. So, since ln X I is a fraction quantity, ln X I is a negative quantity. So, negative and negative will become positive. So, basically delta X is greater than 0 because ln X I is negative. Good that you asked. Now, again we are going to do one more calculations on system and surrounding to get us understand it little bit better. 1 mole of perfect gas molecules at 27 degree centigrade isothermally expands isothermally from an initial pressure 3 atmosphere to a final pressure of 1 atmosphere in 2 ways, reversibly and against a constant external pressure of 1 atmosphere. Calculate delta S, meaning delta S of the system, surrounding, and then total for each path. Okay. So, let us do for the reversible case. So, it is an isothermal expansion from 3 atmosphere to this thing. So, what will be the system's entropy? So, we know the system entropy is from the formula N R ln V f by V I, right. Now, we know from ideal gas system is that P I V I by T is P f V f by T, because it is an isothermal one, which means that V f by V I, V f by V I will be P I by P f, that do not make that mistake. So, it is N R ln P I by P f. What is P I? We know that P I is 3 atmosphere initial pressure and this is 1. So, this is N R ln 3 and 1 mole of gas. So, just take N to be 1, just take N to be 1, R ln 3 is the answer. That is the system entropy. What will be the surrounding entropy? Now, it is a reversible process, right. So, in the case of reversible process, delta S surrounding is just minus delta S of the system. Okay, because surrounding is changing the same way. For example, remember an isothermal expansion for a Carnot cycle, the heat changes, it is isothermally, it is very slow. So, both the system and the surroundings are at the same temperature. So, therefore, the changes are reversible, it can go back to the same value. So, the surrounding is exactly same as the system, the negative of the system. So, delta S total is going to be 0. So, reversible, the idea to show this problem, idea that the problem shows is that for a reversible isothermal processes, the total change in the entropy is 0, because system and surroundings are negative. You are going to see that is not the case when it does at a constant pressure. So, that is there in the problem number B. So, it says that what happens when it expands at a constant external pressure of 1 atmosphere. So, now in that case system entropy, how do we calculate that? It is an isothermal process, remember temperature is not changing. So, we know that ds is dq by t, right, dq reversible by t. Okay. So, what is dq reversible here? It is a constant pressure process changing, right. So, our dq we can get from, because du is 0 because the temperature is not changing. So, dq is minus dw. What is minus dw? du is minus dw by t. Now, what is the minus dw, or rather I should do the integration of that. So, minus 1 by t dw. Now, what is dw? Dw is, the work done at a constant pressure is just P V 2 minus V 1. So, minus P external V final minus V initial. Now, let us write down. So, P external divided by T V f minus V I. Now, we have to calculate what is V f and what is V I. Again we will use the ideal gas formula. So, P f V f by T is 1 minus V I by V f, that is also fine. P f V f by T is R, that is also fine. 1 minus V I by V f. What is V I by V f? P f by P I. Okay. You can do otherwise this one, P I V I by T is P f V f by T, T T cancels, then V I by V f is P f by P I, just the opposite of that. Now, we know the values are 1 minus what is P f? P f is the final pressure 1, initial pressure this thing. So, we are going to get 2 by 3 R. Is it okay? All the steps? See, this I said that B is having at a constant external pressure, and I calculated the changes this way at a constant pressure, but will that be systems entropy? Correct. So, it cannot be systems entropy, because even if the process is happening irreversibly, to calculate the entropy of the system we have to always choose a reversible path. So, that is the idea of this particular problem. See, in the first case, the problem number A, it is happening reversibly. So, both system and surroundings entropies are same, but the second step it is happening irreversibly, but in case of an irreversible process, to calculate the entropy of the system we have to choose a reversible path, which means in the case of B, the system entropy the same one as RLN3, whereas surroundings entropy is negative of this particular quantity. Okay. So, the thing is that the calculation that we showed is that the surrounding entropy is whatever we calculated just now is minus 2 by 3 R, because it is negative value, because it is losing that amount of this entropy, and the system entropy is whatever we calculate by a reversible way, which is RLN3, which we already calculated for the reversible step. So, remember again that entropy calculation for the system has to be always a reversible path, it cannot be irreversible path. So, even if the process is happening irreversibly, one has to calculate the corresponding reversible path. The second example, when it is happening at a constant pressure, that to the final constant pressure, the process is irreversible. However, entropy calculation we have to consider a reversible path, which is already done in the problem A. So, system entropy still remains as RLN3. However, surroundings entropy, first of all it will be negative, and secondly it is calculated the way I have shown here, which is. So, now the total entropy, okay, so let me just so this is surrounding entropy, system entropy is RLN3 for the second problem, problem B. So, total entropy is RLN3 minus 2 by 3 R. Okay. So, here what we are calculating actually is surrounding entropy. Okay.